All right, so section 5.1 is on area and estimating with finite sums. So again, remember, I kind of made the joke last time, sums, we're literally just going to be adding this lesson. But ultimately, what we're working towards is section 5.4, which is on the fundamental theorem of calculus. And that's typically where calculus 1 stops. So the fundamental theorem of calculus is going to tie together ideas of antiderivatives with derivatives. So we want to spend a little bit more time understanding antiderivatives. And if you kind of remember with antiderivatives, we used this little symbol that I mentioned was just an elongated S. And that elongated S stands for sum. So we're going to kind of build up from basic ideas of finite sums. So in chapter 4, we discussed the indefinite integral of f, or that is using this symbol with antiderivatives. So the antiderivative of f of x dx is the collection of all antiderivatives of f. We will first develop of the basis for formulating definite integrals as a construction of finite sums. So we're going to work towards definite integrals, which are just simply finite sums. And then it'll allow us to approximate the area under the graph, the distance traveled by a moving object, or the average value of the function. So those three things are what we're going to understand in this lesson as just finite sums. So let's first start with area. Question 1. Find the area under the shaded the shaded region R that lies above the x-axis and below the graph of y equal to 1 minus x squared and between the vertical lines x equal to 1 and x equal to 0. So you can see we're talking about this region right here. Here's the vertical lines, x equal to 0 and 1. And then, of course, this function, 1 minus x squared, is just an inverted parabola. And we're in the first quadrant right here. So let me just maybe make this question. So we're looking at this blue region right here. The area here, the area of R, is it going to be less than or greater than 1? Let me start with that question right there. Look at that region. If you think it's going to be less than 1, point down. If you think it's going to be greater than 1, point up. I see a couple of you pointing down. I think, Chapel, why are you pointing down? No, Emma, what do you think?
I think it's under 1.
You think it's under 1. Why?
Because if you had the whole area of 1 by 1, it would be 1, but that's not the whole area.
Yeah. So we're going to kind of relate this to a shape we already know. If we had a 1 by 1 square, how would you find the area of a 1 by 1 square? Base times height. So 1 by 1. So the answer here is that it's going to be less than 1. But what is it? Do we have a nice formula for it? Well, not really. So what we're going to do is kind of take that idea of using shapes we already know, and let's go ahead and just maybe divide this shape in 2. So right there in the middle, I'm going to divide it in 2. And what I'm going to do, on the left side of it, I'm going to go ahead and make a rectangle. So right there's going to be a rectangle here. And then I'm going to go ahead and make another rectangle to get this other piece. So you can see right here, as Emma pointed out, if we had a 1 by 1 square, we could figure out the area is 1, but that was definitely too much. So let's go ahead, instead of doing a 1 by 1 square, let's try to just go ahead and start using little rectangles. And if we look at this, we can find the area of these two red regions by just finding the area of the individual ones and adding them. Before we do that, is that going to be an overestimation or an underestimation of the actual area of the blue region? It's going to be an overestimation because we have this little bit of extra right here. So let's go ahead and actually figure out how to go ahead and find this area of the sum of the red regions. So the area of the red regions, let's think about it. We have our first rectangle, so it's going to have a height and a base. So we'll multiply those together. And then we're going to have a second height and a base, and we'll go ahead and multiply those together and add them. And I'm just putting the height first because it's going to better reflect kind of the way the book develops the notation as we go. So we have the area, let's see, H1 is going to just be 1. So it's going to be this height right here, so it's going to be 1. But what about the base? Right here, it's going to just be 0.5, or I think the viewing examples tend to work with fractions, so I'm going to just go ahead and do 1/2. So that right there is going to give me the area of this first rectangle. Everyone okay there? So what about the second rectangle? So we need to figure out the height of this one. Well, the base is pretty easy because if we look at the base right here, we subdivided it, so the base is going to again just be 1/2. But how do we find the height? Any ideas? Realize that the height is on the function. How do you find a value of something on the function? You plug in x to find the associated y. So let me go ahead and write that. We need to go ahead and find this ordered pair to find the height of the second triangle. So this is the height of the second triangle. In order to, let me just kind of put this in words. So we obtain a y value by evaluating f of x. So in this case, x is going to be 1/2. So if we did f of 1/2, just kind of treating this as our function f of x, we get 1 minus 1/2 squared, which is going to be 1 minus 1/4, or 3/2. So this is just going to be the ordered pair, 1/2, comma, 3/4. So this right here, the height of the second rectangle is 3/4. Is everyone okay with where I got that? So let's go ahead and put that in. So that's going to be 3/4. Multiply this. So let's go ahead and continue. So this will be 1/2 plus 3/8. Remember that you multiply the across the numerators and across the denominators. If you were to get a common denominator right here, you would end up with, let's see, we have a common denominator of 8. So I'm multiplying both top and bottom of this by 4. So this is going to be 4/8 plus 3/8, which is ultimately 7/8. Or if you were to write this as a decimal, 0.875. So that is the area of the two red rectangles. It is a couple things to note. We already talked about it. This number is an overestimation. Or you might think about it and the terminology associated with what we just found. It is called the upper sum. The upper sum, because it's an overestimation, and we basically let these rectangles go above the area that we're trying to find. So, any ideas? How might we maybe get a better estimation or a better approximation of the area? Any ideas? Say again. We could use more rectangles. So instead of dividing it in 2, maybe we would divide it in fourths. And it seems like maybe we have a way to make it infinitely small using limits. We're going to get there. Any other ideas on how to maybe get a better approximation? Raul? So there are ideas such as the trapezoidal rule and things like that you won't get until Calculus 2. We just deal with rectangles for now. So using maybe different shapes would also give you a better approximation. Any other ideas on what might give you a better approximation? Emma? We could go ahead and consider using different rectangles. So let's go ahead and consider those two scenarios. So another one, as Emma, you mentioned, we could use the lower rectangles. So let's go ahead and combine a couple of those ideas on the next page. So let's first go ahead in this top triangle, top area that we need to find. Let's go ahead and do the lower sum. So up here, let's go ahead and do the lower sum. So I'm going to take that idea, and I'm going to also take your idea, Luke, and I'm going to go ahead and we're going to just do more subdivisions. Raul, I'm not going to use your idea right now because we're not quite to the to those ideas yet. But it's something awesome to explore and a lot of fun that you'll see in Calc 2 for those going there. So what I'm going to do this time is let's go ahead and let's do 4 rectangles. So I'm going to go ahead and divide this into 4s. And the first rectangle, we're going to just make it using underneath the function. So it's going to be the lower sum. So this right here is going to be my first rectangle. Now, that's good there. The second rectangle is going to be right here above 0.5. So let's go ahead and get that in here. Okay, let's shrink that in. Okay, the third rectangle is going to be here. Again, just maybe keeping this is going to be 0.75, or you could think about it as 3/4. So it's going to be right here. Let me line that up better. There we go. And then the fourth rectangle is actually kind of interesting because if you use your fourth point here at 1, your fourth rectangle, let me make it a little bit larger, that was a little excessive. Let's just do this one. It's right there. Your fourth rectangle, well, is squished because you're using kind of the right endpoint, having it underneath that. So your fourth rectangle has an area of 0, which is fine, but it is technically there as part of the lower sum. So let's go ahead and consider the lower sum now. Let's raise that up a little bit and try to make it look good. It's showing off. It's got to look good. It's a Wednesday. So let's go ahead and see if we can get the upper sum. Let me go ahead and get you started on this one. We're going to need this point. So this is going to be the point 1/4 because we divided 1/2 in half. So that's 1/4. And again, how do we find the y value or the height of that first rectangle? We're going to use what? The original function. We're going to plug in x. So let's go ahead and do that. That's going to be 1 minus 1/4 all squared, which is going to be 1 minus 1/16, or this is going to be 15/16. So let me go ahead and give you a moment to just maybe spend some time processing it and find the rest of these green ordered pairs. And go ahead and see if you can actually go ahead and find the lower sum. While you do that, I'm going to take attendance. But let me give you a moment to see if you could go ahead and find the actual lower sum now that I've got us kind of started. So up on the screen, I do have the work. Let me give everyone just another moment to maybe check where they're at with maybe the answer. These problems, yes, they're a little bit tedious, so it'd be nice if we had some calculus techniques to kind of maybe make these computations a little bit faster. We'll get there. But let me just give everyone a moment to see how they're doing. Does anyone have any questions so far? Yeah, Cadence. How do I get the height? Yeah, so one thing to note how we're basing our subdivision. If you notice that our bases are equally dividing up, so you can see we have a distance of 1/4 along every single scenario, or along every single rectangle along the horizontal axis. Are you okay with that? So once we have that kind of equidistant breaking up of the x-axis, we can find the corresponding the x values. So once you have 1/4, you can take 1/4 and plug it into your function. So 1 minus 1/4 squared is going to give you 1 minus 1/16. And that right there is going to be the corresponding the y value. And that y value is going to be the height of the rectangle. So this right here is going to be the height of the rectangle. So you can see in the second one, this 3/4, I got this by plugging in 1/2. This 7/16 I got by plugging in 3/4, and that will give you the heights of the corresponding rectangles. And the last one, of course, has a height of 0. So, any other questions? Does that help? Perfect. Any other questions? So, that again is called the lower sum, and maybe let's go ahead and emphasize that the lower sum is an underestimation. So at least we now know that the area of the blue shaded region is going to be more than 0.5, because if we look at this, what we have right here is not enough. We're missing this right here. So you can see we're missing some area. So there's one other, there's the idea we can kind of average those two ideas. So if you have the values, you can average them, which I didn't do ahead of time. It would be interesting to see what the averages would be. What was it? So 0.75 and 0.53, so somewhere in the 0.60s. But maybe you didn't want to, it still seems tedious to go ahead and like do the upper sum, then do the lower sum, then average them. So you know what? If we're already drawing rectangles, let's go ahead and just have, instead of the endpoints of the rectangle being on the curve, let's have the midpoint of the rectangle on the curve. Yes?
Why didn't we find like the area of the triangles and then add them together to find the full area
Of the what? Of the curve?
yeah.
Yeah, so we could, and that's essentially what we're doing, but you can see what we have right here is an underestimation. So as someone pointed out, I've already lost track of who pointed out, all I could need to do to get rid of the estimations is just maybe use smaller rectangles. So yeah, we could essentially just use smaller and smaller rectangles, and we will kind of relate that to limits and ask the next section. Right now, we're just kind of doing finite sums. So the last option with our rectangle construction is to use the midpoint. So let's talk about the midpoint rule. So the last one to look at is the midpoint rule. This one is a little bit tricky in the setup, so I'll kind of show you how I set it up, and hopefully that'll help you. But I'm going to just, again, do 4 rectangles. So my setup is going to consist of first dividing it up into 4 pieces. I want 4 rectangles. But what I want is the midpoint of the rectangle to hit right here. Because if I choose the midpoint, you can see right there, I've drawn kind of the grade right there is through the center of the rectangle. So the rectangle I draw is going to be this one right here. It didn't quite do it straight. Let's try that again. All right, I can work with that. So let's just bring that over and bring this down. But you can see now, if you look at this, it's a little bit hard to see. Let's do the next one. So let me also take the midpoint of the next rectangle. I want that one to hit right here at the curve. So let's line that up. And I'm going to draw a rectangle where the gray is going to be hitting the curve. So there's my division line. And now this one will be a little bit easier to see. But if you look at this rectangle right here, notice this piece is a little bit of an underestimation, but this piece is a little bit of an overestimation. So now there's a balance between under and over that'll give us a more accurate result. Does everyone see how we're constructing these rectangles? Awesome. So let's again go ahead and draw the midpoint of the next rectangles, or the remaining rectangles. And let's draw the associated rectangle using that gray line as the midpoint of the rectangle. So we now have 4 rectangles, which we can find the area for using a similar strategy. Again, just to figure out, we need to find the y values here. Careful, that is not quite 1. That's a little bit below 1. This is going to be the point. Well, let's see. If this is 1/4, that gray point is going to be at 1/8. So this is the point 1/8. And if I were to plug that in for the function, I would get 63 over 64. This second point, again, is now going to be, it might actually be easier to think about it in terms of just think about everything in terms of eighths. So it might be easier to think about this second one as 2/8 instead of 1/4. Just helps you kind of iterate through a little bit more naturally. But this would be the ordered pair 3/8, and I did the math ahead of time. This would be 55/64. This point is going to be 5/8, and the corresponding y value is going to be 39/64. And then this right here, the last one, is going to be 7/8, and correspondingly is going to be 15/64. Is everyone okay with where we got those values? Very similar to the previous ones. So just to save me from writing all these numbers tediously in front of you, I'll go ahead and just copy it in, and then I'll kind of give us a moment. Y'all want a moment to write the individual sums? Okay, so yeah, instead of me trying to frantically match in front of 20 of you watching me, I'll throw them up there, but I'll give you all a moment to write, and then we'll talk about it and see if there's any questions. So 63 over 64 times 1/4, 55 over 64 times 1/4. A little typo right here. That should be 39/64 times 1/4. And then the last one is 15/64 times 1/4. You could actually even kind of factor out the 1/4. So if you kind of look at what this 63 plus 55 plus 39 plus 15 is 172 over 64. So you could kind of think about that, because the 1/4 is common amongst all of those. You can just kind of go ahead and add the heights. And then once you add the heights, multiply it by the base, because the base, we're doing equidistant subdivisions to kind of reduce the computational load. And again, when you talk about rules like the trapezoidal rule or the parabolic rule in Calculus 2, you kind of lose that convenience for the sake of accuracy. So ultimately, this is going to be approximately 0.671875, and it is an estimate. It's a pretty close one. And I think, Savannah, you were alluding to this earlier, like why can't we just do more rectangles and ideas like that? Well, because it's tedious. But this table down here actually went ahead and did it. Hold on, let me see. Does anyone need more time with the work right there? Everyone good? Awesome. So this table, you can see we did these fourths, so you can see here's the midpoint, and the ones we did were basically, the first one was the upper sum, so this was 1, and this is what we did. The second one was the upper, then we did the lower sum. So we did those 3 right there, so this table fills out many of the other scenarios. But if you kind of look, if we were to just consider smaller and smaller subintervals, anyone want to take a shot at what do you think the area of that blue shaded region would be based off of this table? Luke? 2/3. Because if you look at this, we have the idea of a limit, especially if we look at the midpoint, you could really see 0.666666675. The area here, it looks like if we were to continue this process, is going to be exactly 2/3. Or it's going to get so close to 2/3, you might as well just call it 2/3. Because at some point, I'm not going to estimate to a 10 millionth place on my calculator. I'm going to just call it 2/3. So that's the idea that we're going to work towards, known as the definite integral. But for now, we're just going to learn about them in terms of sums and some of the other applications. But does anyone have any questions on these right here? But if you understood this idea of just kind of considering small and small intervals, it's going to just show up in a couple of different scenarios. So the first scenario is with area. The second one is related very much to like rate of change, so velocities, accelerations, jerks. The distance traveled scenario. So let's go ahead and look at example number 2. There's a lot of words right there. So let me just go ahead and give you maybe about 15 to 20 seconds to read that once or twice to yourself to kind of get yourself oriented to the problem, and then we'll talk through it. All right, let's go through it together. Suppose we know that the velocity function v of t, I'm going to just kind of write down this information as I go. So v of t is going to be 10t minus t squared, and this is, the units are feet per second. So the velocity function of a car that moves down a straight road or a side road without changing direction. So we have our side road without changing directions. So I'm going to just kind of, here's my road. It's going to be straight. And we know that the car, let's see, here we go. We got my car. I am a great artist. Nope. There's my car. Let's give him a little, it's like a truck. Anyway, is traveling in this direction. So let's see, this is time 0. So this is time 0. Let's see, how far did the car travel during the 3-second interval during the trip, say from 5 to 8? So we're told to use the summation techniques from the that were just described to estimate the distance. How close to the sums come the exact value of 66 feet? So let's get to the right interval. So there's going to be 1, there's going to be 2, there's going to be 3, there's going to be 4, there's going to be 5, 6, 7, and 8. In the region, or the part of the trip that we're concerned about, is this little distance right here from 5 to 8. So, funny looking road, has little tick marks and numbers on it, but I think it illustrates the problem well. So we need to go ahead and figure out, okay, so this is already pretty nice. So let's just go ahead and use a time interval, or delta t, of 1 second. And of course, to figure out the velocity at that time, we have a velocity function. So I'll go ahead and just make a little statement here. It says you can either use the left, middle, or right of a subinterval with the v of t to find the velocity at time t. So you have some choice whether you're using the left, so whether you're going to use 5, 6, 7, whether you're going to choose some value representative in the middle, or you're going to use the right. For the sake of simplicity, I'm going to go ahead and, for this problem, let me change it to red just so we can see that. Green is more of a general statement. For this problem, I'm going to just choose to use the left endpoint with the velocity function to figure out how fast the car is going at a certain time. And again, once I know how fast it's going at each of the times, I can just go ahead and add that with the time, or multiply that with the time elapsed, which is 1 second, and that'll tell me how fast it's traveled. So let's go ahead and figure out then distance traveled. Distance traveled. This is going to be equal to how fast it is going at time 5 times how long you are going at that velocity. So we're kind of assuming for that 1 second it's not changing velocity. And kind of that same principle. The shorter your delta time is, the more accurate that you're going to have. But then we're going to consider the velocity at time 6, and we're going to multiply that by some time interval to figure out how far it went. And then we'll have the velocity at time 7 multiplied by the delta time. So this is going to just be, let's see, our function is up above. So it's going to be 10 times 5 minus 5 squared times delta t is 1 plus 10 times 6 times, minus 6 squared times delta t, which is 1, plus 10 times 7 minus 7 squared times 1. Everyone okay with where we got those values, or anyone need me to repeat where they come from? So if you were to go ahead and do this, work this out, it works out to 70 feet. So the distance from here to here is, of course, 70 feet. We were given the situation that the car was not like reversing or anything. So there is a little bit of a distinction we had to make. But again, emphasize this is an estimate or an approximation. This is not exactly how long or how much distance was traveled. To figure that out, we would need to use smaller subintervals. Because again, we're kind of ignoring that during that 1 second, the car may have been accelerating or deaccelerating. We're just kind of saying for that 1 second, it was going velocity. So, but you can see, same principle. We're just using some function to plug it in Cadence. It may be a little more obvious with this one. Like this is the same thing we did earlier. We would just plug it in to find the height of the rectangle. Here we're plugging it in to find the velocity at a certain time. Any questions on this example? Okay. On the next page, we do describe a little bit more the difference between displacement and distance traveled. So recall that the displacement is the change in position. So like you could think about like, here, let me do it over here. Displacement, let's say you start here. Let's say you go 20 feet there, but then you go 10 back. So this right here, 10 is your displacement. So 10 is displacement. But the distance traveled, so the distance traveled would be the distance traveled is, anyone want to take a shot at it? 30, yeah. Because it's the 20 forward and then the back. So does everyone see the difference between displacement and distance traveled? Distance traveled accounts for you reversing. Displacement is how far you were from your original starting point. So recall that displacement is simply the change in position. In the previous example, we knew that the car did not turn or change direction. Hence, the displacement and the distance traveled were equal, because it told us that it was not changing directions. If the object changes direction one or more times during the trip, we need to use the object's speed. Does anyone remember how we find the speed of an object? Grace, I haven't heard from...
Absolute value of velocity.
Yeah, absolute value of velocity. So very good. I'll just try to get a variety of answers. So remember the speed is the absolute value of velocity, and use that to find the total distance traveled. So we have the following equation where n is the number of subintervals. So you can see right here, the only difference is when you're looking at distance traveled, you do need to go ahead and there's a little typo here. The time is not in the absolute value. Let me go ahead and correct that. So this should be the absolute value, and there shouldn't be one there. So a little typo in the notes right there, that the delta time, again, you can think about that as just being factored out, and you can just add the sum of the velocities at the time, which works out really nice. So a little typo there, sorry about that. Any questions about difference between displacement and distance traveled? Okay. So then the last scenario where this idea of finite sums shows up is with the average value of a non-negative continuous function. Talk about just liking their adjectives. So we'll drop this non-negative idea in the next lesson or two. For now, we're going to assume that is the function we're talking about is always going to have positive values, so you don't have a cancellation of areas. So think about, we already have an idea of average. The average value of a collection of n numbers, x1, x2, up to xn, is obtained by adding them together and dividing by n. You could think about this like this little scenario here, where you have like a discrete, meaning you could like count it 1, 2, 3, so on. So let's suppose, like for example, we have 5 tests in this course. So if you want to know your test average, you add together your tests, divide by the number of tests there are. So the scenario that this first line is saying is, for example, think about just like course test average. But the thing that was with that is you can't have like, assuming you kind of notice how I grade, I don't like 0.5s really. So, I mean, your grades are discrete values. They're integers. So 85, 100, 93, 72, whatever. But this is what we're going to be able to do with finite sums. What is the average of a continuous function on an interval, say a to b? Continuous functions take on infinitely many values. For example, what does it mean to say that the average temperature in Lakeland on June 7th, 2017 was 80 degrees? So you can see right here, so you can see right here, June 7th, which just happens to be our anniversary, although we were made in 2013, but still, June 7th. I made it was a good choice because 6 plus 7 is 13, so I could always remember the year. Anyway. Just how it happened. We didn't plan it that way. Not much of a math nerd, maybe. Anyway, so if you think about it, there was the temperature during the day. Of course, it was thunderstorming because welcome to Florida in the summer. So you had a high of 84 and a low of 71. But what was the average temperature? What would you all say? What was the average temperature on that day? Destiny, what do you think?
78.
So 78. So you put it up here. So you didn't just divide. So you kind of just divided these and kind of split the difference. But it seems like we spent a lot of the day really hot. Welcome to Florida, right? A lot of the day is really hot. So it's not as easy as just adding up the high in the middle and then dividing it by 2, because you're neglecting that the day sometimes is a little hotter during the day. So that's what we're going to get to down here. Let's maybe simplify this problem. How should we define the average value, again, of a non-negative function? Because if you have negative, there are cancellations of area. More on that in 5.3. So it's pretty easy. If you think about this, let's think about this first function, a. So if you look at a right here, so there's a. F of x is the constant function c here. So if something does not ever change, what is the average? So whatever it was at. I mean, there's no up or down. It's just what it's been. So if we look at this right here, the average here, the average of, let's say, this f of x is going to be, well, not just c. It's going to be, because if you consider the c, that's going to talk about, this is be like 1 times c, but you have to consider it over the course of this time frame. So what you're going to do is you're going to take the area and you're going to divide it by the interval, the distance of the interval. And that's what it's saying down here. The average value of a constant function on A to B is the area of the rectangle divided by the length of the interval. So this is kind of giving us something to work with, but of course, not everything is constant. So let's consider B. In B, we have some function g of x. And the way that the book describes this, and you could kind of imagine, is all that's happening with g of x is, imagine that is a fish tank. Does anyone have fish right here? Anyone have fish? What happens when you pick up the fish tank? Does the water? The water sloshes around. But does the water change, assuming you're very steady and you're not dripping? It's going to stay the same. Yeah, you don't want the fish falling out, so you don't want any water sloshing out. So you can imagine what's happening is like basically we have water sloshing. That was a fun word, slosh. Slosh, okay. But what you see right here is that the average for this g of x is actually the same as the average for f of x, because the water does not spill out. But you can see there's some low, there's some high, but the average does not change, and you can see that by the dashed green line. So really, how do we then find that area? Well, that's how we did it the first part of this lesson. You just are going to have to subdivide it into rectangles. So let's go ahead and kind of write a formula here. So the average of a non-negative continuous function is going to be the area under the curve, and it's going to be divided by the interval length. So the interval length. So how you find the top part is just you're going to estimate this with sums. Estimate with sums, and we'll do an example on the next page before we wrap up. And the bottom part is just going to be endpoints. Subtract the endpoints, b minus a. But this right here is a formula, more or less, so you may want to just box it in or something to kind of emphasize that this is a general method right here. This is how you find the average of a non-negative continuous function. That's fun. That's like so. Any questions from this page? Anyone still need time here? So let's just make this idea concrete on the next page. If we didn't, that would be a sin, so might as well work with sign. Anyway, end of class. What can I hope for? Estimate, keyword, the average value of this function on the interval from 0 to pi. Again, notice from 0 to pi, sine is a continuous non-negative function. So what we could do is, it's 2 parts. First part, use it's already set up for us with the rectangles. So let's go ahead and use the upper sum with 8 rectangles. Come on, that was mean. 8 rectangles. It is what it is. That's okay. To keyword estimate. This is not the exact area yet. Is it over or underestimate? It is an overestimate because we have that little extra to estimate the area. So again, keyword, this is just an estimate. So the area here, I went ahead and did this ahead of time, but realized that this would be pi over 8. This would be 2 pi over 8, and so on. So the area is going to be sine of pi over 8 plus sine of 2 pi over 8 plus so on. I'm just going to start introducing some kind of ideas to sine of 8 pi over 8. And again, these are all equidistant, so I'm going to consider this being factored out as pi over 8. So let me give everyone a moment to kind of write that and process what we did. I cheated a little bit. Once you've noticed the pattern, you notice I'm counting by pi, 2 pi, 3 pi, 4 pi. So these 3 little dots read so on. More on this in the next upcoming sections. But this idea of like, hey, I don't want to put all of them there. And again, I've already factored out the pi over 8 because each of these are going to, the distance or the change in x will be pi over 8. I did that ahead of time, and this works out to be 6.02 times pi over 8, which is approximately 2.364. So that is the area. Are we done? Have we found the average value? No, we have not. We have found the area under the red rectangles, so an estimate of the area of the curve. So what we'll then do to actually find the average, we're going to take this 2.364, and what are we going to divide it by? Anyone? I've heard from you, Grace. Let's see. Anyone? Class doesn't end until someone I haven't heard from answers. I've actually heard from a lot of you. Alfred, do you think you know what the denominator goes there? It's going to be the difference of the endpoints. Grace, I'll go back to you because everyone's like, please let me leave. What do you think, Grace?
The length of the interval.
So which would be pi minus 0, the length of the interval. So this ultimately works out to approximately 0.753. I know that's tough after 50 minutes of new content. Does anyone have any questions? This is the average value of this function. You can see it's right about there. So a little bit on the high side because it spends a lot more time up at the top than it does at the bottom. Does that make sense? Yeah, Destiny?
So why did we use the upper sum instead of the mid sum?
You could have used the midsum. It's just how the problem was set up for us. It just already had the rectangles there, so we'll use what we have. So, yeah. Any other questions? Okay. Have a great day, everyone. I will see you all tomorrow. We'll pick up with section 5.2. Have a good day, everyone.